Hello, today we will look at morphing of aircraft configurations. In this image you can see a lot of examples of how morphing has been proposed for various types of aircraft. Let us first have a basic understanding of what exactly is morphing. Morphing basically is metamorphosis, that is the genesis of this word morphing, and the dictionary meaning of metamorphosis is to cause to change shape. Now as school students we have heard about the metamorphosis of larvae into butterfly, etc. Morphing aircraft is an aircraft that changes its shape during flight for some improvements. Now these improvements can be of various types. We will look at some of them in a few slides ahead. The inspiration for morphing has come from our observation of the nature around us. Two examples are the honeybees and the bumblebees. Let us have a look at how honeybees morph themselves. Here is one more example from nature, that of the bumblebees. So there is a joke which goes that the bumblebee has not done any course in aerodynamics or flight dynamics, and as per the theory the bumblebee is not supposed to be able to fly, but the bumblebee has not done any course and therefore it can fly. Warping is not new. In fact, the first aircraft to successfully manage heavier than air sustained flight on a powered manned system, the Wright Flyer 1, that also had warping. Let us see a small video clip about the Wright brothers. The Wright Flyer employed warping for seamless flight control, as you must have seen in the video clip also, and you can also see in this image which shows that the controls were such that the tips of the wing were warped to give the action that we get from the ailerons, that is the roll control. The biggest inspiration for morphing comes from birds. Birds demonstrate a fantastic variety and levels of morphing. For example, birds change their shape from takeoff to cruise mode by changing their sweep, As you can see here, at different speeds the same bird puts its wings in different configurations. Okay. So, as we know from basic aerodynamics, the higher speed is suitable for higher sweep is suitable for flight at higher speeds. So, by changing the wing sweep. Let us have a look at a very interesting video in which there are 5 birds which will launch from a particular location in different configurations, and the best one is the last one. So, as you must have seen, the last bird was able to launch and then turn its orientation midway during the flight. Birds also go from cruise to dive mode by changing their wing profile. So, the picture on the right shows a sequence of images shot of a garnet when it goes into a dive to fish, and this is a close up of the same picture, but the beauty is appreciated only when you see this happening in slow motion. So, I am going to show you a small video clip which will capture the motion of the garnet as it converts its wings from low sweep to very high sweep when it goes into a dive. Watch this.
Every dive subjects them to enormous forces. The slightest miscalculation could be fatal.
So, let us look at morphing of wings in eagles. Okay. Eagles are also very well known. Now, look at this particular picture in which you see that the wing tips have these 3 deflected feathers. They are acting like the winglets. Look at the landing gear, how beautifully it is oriented. Okay. Here you see an eagle changing its configuration midway to turn. This is an eagle which is on an approach to land. So, this is how it comes in at very high angle of attack to land. It takes its wings very much behind, and then finally it can perch on a small stone. So, the eagle demonstrates morphing of a very high order. No human created device can demonstrate such a beautiful amount of morphing. What is the need for morphing? As I said, morphing is shape change for improvement. There is a constant quest for improvement in aerospace engineering. We are looking for multi-role aircraft which are optimum in all the roles, not that you use it for one particular role optimally and in the other roles it is suboptimal. No, we want it to be optimal in all the roles. We would like to have improved efficiency in all flight conditions, not just one. So, for example, we would like to maximize the lift over drag coefficient, we would like to maximize the NZ so that we have much better turning performance, At the same time, we would like to reduce the drag coefficient, we would make it lighter by reducing the max takeoff weight, and also we want to reduce the fuel consumed in the mission. So, many of these requirements can be conflicting, but we want to meet them simultaneously, and one way of doing this is to morph the configuration. There are some benefits of morphing. One is there can be improved aircraft performance. So, there are two distinct ways or two distinct approaches to morphing. One of the aim is to improve the aircraft performance by expanding its flight envelope. For this, we carry out morphing at high amplitude but low frequency. By this I mean that you do it once in a while, that means low frequency, you do not do it regularly, you do it few times in the mission, but when you do it you have high amplitude, which means the amount by which the aircraft morphs is quite large. Another application of morphing would be to replace the conventional control surfaces so that we have improved performance and stealth, or we could reduce the drag, which leads to an improvement in the range. The other application of morphing could be to reduce vibration or flutter or to control the flutter. Now here we have high frequency but low amplitude, that means we morph almost all the time, but the amount of morphing is very small. The problem is that these benefits of morphing do not come free of cost, there is no free lunch. Okay. Whenever you go for morphing, there is an increase in the cost, complexity and weight, and therefore you have to decide whether to morph or not, keeping in mind that the benefits because of morphing should be more than the problems because of the increased cost, complexity and weight that are created because of morphing. It is not easy to morph, there are several challenges. First question is, what do you morph? Do we morph the wing or the tail or the engine or the fuselage? Please note, even engines are routinely morphed because the nozzle, for example, you know, of the jet engine aircraft is of a variable diameter. So, the diameter is reduced when the jet exhaust velocity is increased. Similarly, there are inlet guide vanes which also are going to change at some angle, right. Sometimes they are fixed, but they can also be actively moved. Wing, tail, engine, there are many choices. Okay, let us say we decided that we have to morph the tail. Then the next question is, how do you morph? Do you morph using a mechanism? Do you morph by having a loaded structure in which the loads themselves cause the deflection? And when we do this, there are conflicting need for rigidity and flexibility. From the point of view of rigidity, we want the aircraft to not have any flexible parts or parts which can be easily deformed, but from the point of flexibility we need to have parts which can be easily deformed. So, there is a conflicting requirement for rigidity from the structural point of view and flexibility from the morphing point of view. The next question is how much to morph, how much area, what wingspan or how much sweep or how much camber should be changed, because as I mentioned the benefits have to outweigh the costs, complexity, weight and the negatives. Morphing happens also in current aircraft. Flaps are everybody knows about flaps. Okay. You can see these are the flaps which are the surfaces mounted on the trailing edge of the aircraft. This is another view of the flaps. You can see that not only do they deflect downwards, they also create gaps between them. These are called as slotted flaps. Okay. And there are also flaps in the leading edge flaps. As you can see, this aircraft, the leading edge flaps are deflected downwards. So, you have trailing edge flaps, leading edge flaps and you have flaps with slots between them. So, therefore, this is not something new. Okay. Similarly, there is an example of morphing of the nose shape in Concorde, where there are 4 specific positions at which the nose of the aircraft can be deflected to. So, let us watch a small video clip which explains these 4 positions and what the purpose is. Okay. So, we saw that there is something called as a visor which also can be retracted and extended. It covers the windshield, and there are some situations in which the visor is retracted, in some it is extended. We all know also about variable sweep wings. This is not something new. So, variable sweep, here is an example of variable sweep in which the wing can have various positions, and in our own country we have had experience of operating this aircraft MiG-23 and 27M. It also has got 3 specific positions at which the wing sweep can be created. There is a 16 degree 45 minutes position for the low speed flight takeoff and landing. There is an approximately 45 degree sweep for transonic maneuvering and flights and during maneuvering flight and transonic flight, and there is a 72 degree sweep for the high speed dash. Let us see a small video on how this is achieved in F111 using a lever that the pilot deflects. So, this technology is not new, it is there for a long time. We also have variable camber. Okay. In variable camber such as this aircraft, the F-18 Super Hornet, you can actually change the camber of the wing to a desired value at various mission segments. But this experiment was ultimately not very successful, and it was concluded that the cost and complexity and the weight because of the morphing on a big aircraft like this by variable camber is more than the benefit. So, it was an experimental aircraft, but it has not been implemented in any production aircraft. Morphing is possible using some structural technologies. One is you can change the platform using rigid mechanisms. Okay. For this you can have extension of wing, you can fold the wing, or you can sweep the wing. Or you may have compliant mechanisms, which provide camber and twist, okay, by having loads acting on them. You could also have vibration control systems which are usually based on directly applying some force. And you can also have shape control systems where there are actuators which affect the shape change and there are some sensors on board to measure the actual deflections. So, here is an example of morphing using rigid mechanisms. You can see this is called as a gull wing. So, these levers which are projecting outside, you can use them to deflect them to create these kind of morphings. Similarly, when you go for compliant mechanisms, you usually go for these when there is a small amount of structural change, like when you want to have twist or camber change or an asymmetric wing change. So, an example of this is F111 mission adaptive wing, which I already spoke about, that used compliant mechanisms. So, those are basically systems mounted inside the structure which achieve twist, camber and asymmetric wing changes. The current research on morphing is focused on smart materials, adaptive aeroacoustics, smart controls and also telescopic wing. So, here is a short film by NASA which talks about what are the aims and ambitions of NASA in creating morphed aircraft. Shape memory alloys is one structural technology which is very useful in achieving morphing. Mostly it consists of piezoelectric devices and some kind of a sometimes some kind of a truss structure. So, here is an example of a shape memory alloy. So, you can roll it and keep it in this condition for ease in transportation etc. But when you apply either some electrical current or some temperature, it has a memory of a particular shape, in this case the aerofoil shape. So, it will become an aerofoil shape when you put it at particular temperature and it will come back to this or you can roll it back to this particular shape when you remove that particular input. There is a company called NexGen Aeronautics which has experimented with morphing on small UAVs. The MFX-1 UAV, as you can see on the screen, was to change the wing area, to change the wing sweep, mean aerodynamic chord and the wing aspect ratio. And also it had asymmetric morphing, as you can see only one wing is changing its sweep. So, this is an example of how the aircraft can have two different sweep positions and also slightly more slight increase in area. The MFX-2 UAV which came the next year, it had a flexible skin wing. It was seen that around 40% change in the wing area, 73% in wingspan and 177% in the aspect ratio was obtained in this particular aircraft. NASA is currently working on a project called as a MADCAT project, which stands for Mission Adaptive Digital Composite Aerostructure Technologies. In this particular project, which is being done at MIT and California University. So, you can see that the wing is created through an assembly of various small structures like this, and at the nodes we have some sensors. Okay. So, you can actually deflect and deform this particular basic element into any shape you want, and this is an example of a wing made up of many of these small structures, and here is a short film that describes the aim and the current status of this particular project.
Many of us know that airplane wings consist of a multitude of moving and stationary parts. Ailerons, flaps, slats, spoilers. The wing changes its form throughout the flight, and there is an optimal shape of the wing for every stage of the flight. This approach to design of wings exists from the very birth of aviation. NASA and the Massachusetts Institute of Technology have recently published materials about a completely new approach to aviation. They have presented a MADCAT, a wing that can continuously change its shape depending on aerodynamic conditions. MADCAT consists of thousands of small, triangular blocks combined into a lattice-like structure. These blocks serve as ultralight Lego bricks. One can build and rebuild an object, giving it a new shape for specific tasks at any time. NASA and MIT developed a technology of composite injection molding, in which the casting of one block takes 17 seconds, instead of the previously needed several minutes. The solution becomes quick and easily scalable. It's still far from the stage of industrial production, but NASA has been testing sensor-equipped wings to monitor the airflow around the wing and continuously adjust its shape.
Now, this is an example of a project which has gone from conceptualization in 1998 to actual testing on an aircraft in around 2015, I think. So, this is the flex foil active compliant trailing edge, which was invented by Professor Sridhar Khota of Mechanical Engineering Department of University of Michigan Ann Arbor. You can see here that the wing does not have any discontinued parts. Normally when you deflect the flaps, they go down, so they create a cavity. Here there is a flexible membrane attached to the root, so they are not going down, they are just deforming. So let us watch a short clip on this concept which explains how this concept went from the initial idea to the reality through various stages.
In the spring of 2015, the Air Force Research Lab at NASA successfully completed tests to realize a decades-long quest in aviation: to seamlessly change the shape of aircraft wings in flight. This breakthrough technology will usher in a new era in aviation design. But it wouldn't have been possible without the vision, funding, and persistence of the Air Force Small Business Innovation Research Program.
As you increase the strain.
In 1994, Dr. Sridhar Khota was an associate professor of engineering at the University of Michigan. He was working on an idea inspired by nature called distributed compliance. Human engineering uses rigid materials and joints for strength. Nature is different.
In designs in nature are strong, but they're flexible. And you can see them in trees and sharks and elephant trunks and millions of other examples. The idea of distributed compliance is to distribute the compliance, the flexibility of the material distributed throughout the structure so that no one part is overstressed.
It occurred to Dr. Khota, by distributing the force deformation, it would be possible to create a seamless, morphing aircraft wing. This was the idea he brought to the AFRL.
We saw it as an opportunity to be able to achieve the benefits of wing shape morphing and to be able to do it very efficiently.
So I applied and I received the SBIR Phase 1 contract in 1998. And the purpose of that was to demonstrate the feasibility.
Dr. Koda was able to do a detailed design, actually fabricate a compliant leading edge surface, and test it in a low-speed wind tunnel.
So this is the prototype we built with the leading edge that can droop, change the camber all the way to 10 degrees. So that was the outcome of the Phase 1, where I not only demonstrated it can be done, and by looking at the calculations and the prototype, they could readily see that it can actually be scaled.
In 2000, Dr. Koda was awarded a Phase 2 SBIR contract with which he formed a company, Flexus.
So in Phase 2, we were looking at specific applications. We looked at a leading edge fighter structure. We looked at a trailing edge structure of a high altitude, long endurance vehicle. And we also looked at trailing edge structures for transport aircraft.
And this is one of the designs that we prototyped. Here is a shape adaptive trailing edge.
As Flexus successfully completed one Air Force challenge, they were given another.
We built this prototype to evaluate the structural feasibility of this design.
By 2006, they had met every challenge, and it was time to take the technology out of the shop and into the field.
So we took our wind tunnel model and we attached it to the bottom of the White Knight aircraft, and taking it to altitude and Mach number that was relevant to the application being studied.
So you have this aircraft flying out of Mojave Desert at whatever 110 degrees Fahrenheit and soaking all the heat, and a few minutes later it's up at 55,000 feet and experiencing minus 40 degrees or minus 50 degrees temperature. So the temperature changes and how the material is going to react and how the actuator is going to react is something we wanted to test it out. And the other part was the aerodynamicists have known for a long time that if you have a one continuous surface, you can change the lift conditions without increasing the drag. While that was all theory, the flight test results have actually confirmed that we can change the lift conditions with minimum or actually no drag penalty.
So we successfully demonstrated the structure being actuated at relevant conditions, including Mach number, temperatures, due to changes in altitude and flight conditions.
It was now time to take the final step, an SBIR Phase 3, which would entail incorporating the Flexus technology into an aircraft and flying it.
So AFRL approached NASA with the idea of replacing the flaps on a Gulfstream 3 test bed with a compliant trailing edge surface.
So here it is, the final product. 20 years after my first visit to Air Force Research Labs, here it is ready for flight testing by NASA.
The seamless compliant wing was attached and instrumented to the Gulfstream 3 at NASA's Armstrong Flight Research Center in California. 22 rigorous tests were scheduled between November 2014 and April 2015.
We evaluated the structure to very large deflections consistent with takeoff and landing type conditions, and to smaller deflections consistent with cruise trim applications, as well as load alleviation and vehicle control.
It passed all 22 tests with flying colors.
None of this would have been possible without the Air Force SBIR contract. They had the vision to recognize the value of this technology actually on day one when I first visited them in 1994. And they also supported us throughout and worked with us very closely in maturing this technology.
So it's taken us 17 years from the beginning of Phase 1 to the completion of Phase 3. What does this mean for aircraft of the future? It means we're going to fundamentally change the way we design those aircraft.
The Air Force is now applying the technology to a KC-135 under an agreement between Flexus and Boeing. When further commercialized, the Flexus technology will lead to billions of dollars in annual fuel savings, reduced manufacturing costs, and quieter, lighter aircraft. A breakthrough in aviation made possible by the Air Force Small Business Innovation Research Program.
Let's look at the challenges in morphing. You have to ensure the structural integrity of the aircraft during morphing. The actuation forces that you require should be realizable. The load bearing surfaces have to be aerodynamically smooth, so you cannot have any projections, etc. You also will need very efficient engines for low and high speed operation, and the control surfaces will become coupled, okay, because morphing will change the control surface configuration also. And as I mentioned in the beginning, morphing is carried out so that we can fly the aircraft optimally in multiple flight regimes. Let us move on to one special example of morphing, which is inflatable wings for UAVs. Okay. So, here the wing is packed inside the fuselage like this, so that you can launch this UAV like a barrel or like a small rocket kind of a thing, and then when needed the wings will come out after they are inflated. So, as I mentioned, this is an example of inflatable wings. They are made up of flexible material and they achieve rigidity by gas, air or air pressure. Okay. You can use it in hand or gun launched and aerial launch vehicles such as this one, which is mounted below this UAV, and they can be deployed on ground or air. So, for example, you can launch it like this and then when needed the wings will come out. Let me show you a small video. So, as you can see, the wings can come out when needed. The wing structure generally is of baffle type, where there are these partitions created. You can see this is an example of wing baffle structure, and this is the finger like bladder. Now, there are many ways of doing it. One way could be that you make the baffle separately like this, like a fingers, like bladder system, and then you insert it inside this particular structure and then inflate the wing. Or you could also have only vertical members joined here, which are a part of the envelope itself. Now, this goes into very deep levels in material science. Some of the candidates are PBO and Xylon because they are sensitive to compression failure and they degrade when exposed to various wavelengths of light. So, they are good, but they have these limitations. Kevlar is also very popular as an inflatable wing material because it has got high strength and it is much affordable. And Vectran is another proprietary material which has excellent resistance to flex cracking and it has got negative environmental sensitivity. So, if you are interested, there is this paper which can be located and read for more detailed information about the materials used for the inflatable wings. What are the benefits of inflatable wings? First of all, it gives impact resiliency to the aircraft. Many UAVs they break when they hit an obstacle during their flight, but in case of inflatable wings probably you can make it very much resilient to impact. It gives you high packing efficiency. As an example, you can see that either the whole wing can be stored inside the fuselage like this, or it can be rolled and packed in a very small volume. It has been seen that inflatable wings are a low cost solution of morphing and the wing is reusable. The best part of inflatable wing is that morphing is easy, but there are also some limitations. One is there is a potential for leakage because it is an inflatable structure. You require a thicker aerofoil because you cannot have very thin and sharp edge aerofoils with inflatable wings. The aspect ratio is limited because you cannot make it very slender because the air pressure will not then equally distribute towards the edges, and you have to always carry some inflation system which is either gas or air based, and the mass burden of that adds to the mass of the whole aircraft. An important aspect in inflatable wings is rigidization. What is rigidization? Basically we need to stiffen the wing fabric using an external agent after you deploy it. Why do we need it? There are several reasons. One reason is that this will help us to reduce the leakage. It will also make the wing stiffer so it can carry more loads. It might be able to allow us to make thinner wings if we rigidize the surface, and the inflation and the system would be smaller and lighter if we have rigidization of the wing. Let us look at some applications of inflatable wing UAVs. One good example is Tiger, which is the tactical grenade extended range. In other words, it is a small, you can say a small remotely controlled aerial vehicle which is a carrier for a hand grenade. So, it increases the range of the grenade. There are other examples where you can see you launch it like a rocket or a missile and then you bring out the wings when needed to make it fly like an aircraft. So, thank you for your attention. Here is a photograph of an aircraft which was mostly consisting of inflatable structure except for the engines and the forward portion. This aircraft could be inflated on the spot by a pilot and then flown. The basic idea of this was to rescue people from the enemies during the Second World War. But when the proposal was given to the US Air Force, they said that we do not have any use, we do not have much use for an aircraft which can be brought down by a bow and arrow. So, I will be happy to answer any questions on the discussion board. Thank you.